Welcome to ATMOS 5000, day number 34. We're focusing in on the Stull Chapter 10, sections 10.4 and 10.5. We're going to be looking at the horizontal equations of motion and putting equations on the different components of the horizontal equations of motion, and then we will look at balances that can happen in the horizontal with regards to the geostrophic and gradient winds, what happens in the boundary layer when we add friction, and a special type of wind balance called the cyclostrophic wind. So here we have the horizontal equation of motion. It's basically an application of Newton's second law of motion, that force is equal to mass times acceleration. In this case, the net force divided by the mass is equal to the acceleration, and the acceleration, of course, is defined as the change in velocity over change in time. And that's going to be equal to the acceleration due to the pressure gradient force, plus the acceleration due to the Coriolis force, plus the acceleration due to the centrifugal force, plus the acceleration due to the advection of momentum in the Eulerian reference frame, plus the acceleration due to turbulent drag. So this is very much a shorthand notation, and each one of these shorthand notations will have to be fleshed out into its own equation. And once we have all of the equations for the individual component accelerations, then we can recombine them into a complete horizontal equation of motion for the U and V wind components in the I hat and the J hat directions, the east-west and north-south directions. And these will be basically differential equations, which we're not going to be able to solve, but you'll get the idea from the equations of putting them all together. So let's take a look at the pressure gradient acceleration first. So the top term, f of x from the pressure gradient divided by mass, is the acceleration in the east-west direction, also known as the I direction, and it's equal to minus 1 over the density of the air times the pressure gradient, the delta P over delta x. And then the exact same thing for the acceleration in the y direction, which is the north-south direction, which is the j direction, is going to be equal to minus 1 over rho times delta p over delta y. So to understand the acceleration, you just have to understand how the pressure is changing in the x and y directions. And of course, it's the pressure gradient force that is driving the winds. If we look at the centrifugal acceleration, the centrifugal acceleration is equal to the wind speed squared divided by the radius of curvature. Now, when we convert this into the I hat and the J hat directions, i.e. the east-west direction and the north-south direction, we have to include this directional sign factor, S. So the acceleration due to the centrifugal force in the east-west direction is equal to plus s, which is that sign factor, times the velocity v, which is the north-south velocity, times the magnitude of the wind, divided by the radius of curvature. And that s factor is either going to be a plus or minus 1, depending upon whether or not the winds are circling a lower high pressure and whether or not that lower high pressure happened to be located in the northern or the southern hemisphere. And so for the y direction, the j direction, the north-south direction, the acceleration due to the centrifugal force is equal to minus s times u, which is the east-west wind, times m, which is the magnitude of the wind, divided by the radius of curvature, r. So here we have the Coriolis acceleration. So we have the two different components, the east-west component in the I direction and the north-south component in the j direction. Let's take a look at the east-west direction first, and that is going to be equal to minus 2 omega cosine phi times w plus 2 omega sine phi times V, which is the north-south wind. And let's take a look at those. The omega is the angular rotation of the Earth, which is essentially 2 pi divided by the 86,400 seconds, which are in 1 day. So that's the angular rotation of the Earth. Phi is the latitude. And W is the vertical wind speed, and V is the north-south wind speed. And since the north-south wind speed is much, much greater typically than the vertical wind speed, most of the time, the approximation for the Coriolis acceleration in the east-west direction is generally taken to be the Coriolis parameter Fc times V, which is the north-south wind. The Coriolis parameter Fc is equal to 2 omega sine phi. So it's a function of latitude. And then for the north-south direction, the north-south acceleration due to the Coriolis, and that's going to be equal to minus 2 omega sine u, which is equal to minus the Coriolis parameter times u. The horizontal advection acceleration is only available in the Eulerian reference frame, not the Lagrangian. So if we are at a fixed location, the acceleration of the wind is going to have a component which is the advection of momentum. And in this case, the advection of momentum in the east-west direction is as stated here, minus u times the gradient of the u wind in the east-west direction, the delta x, minus v times the gradient of the east-west wind in the north-south direction, delta y, and minus w times the gradient of the east-west wind in the vertical, delta z. And you have the same sort of expression for the horizontal advection acceleration in the north-south direction. The only difference is that we're looking at the gradients of the north-south wind as opposed to the gradients of the east-west wind. So friction is a term which is really important near the Earth's surface. It always acts to slow an air parcel down, and it always acts to oppose the motion. And the more rough the surface is, the stronger the frictional value. And that roughness is a function of both the terrain in terms of mountains or flat. It's also a function of structures such as buildings. It's a function of vegetation, whether you have trees or sagebrush or grass, or the surface, whether or not it happens to be land or water. The friction layer is the lowest part of the atmosphere where the atmosphere is being influenced by that frictional term, and that's referred to as the planetary boundary layer. And once we get above that planetary boundary layer, then friction is negligible in the atmosphere. So turbulent drag or frictional acceleration is really controlled by a turbulent transport velocity, Wt, which is kind of a parameterization for the turbulence. And so here we have in the east-west direction, f of x over m, which is the acceleration due to turbulence, is equal to minus Wt, which is that turbulent transport velocity, times the wind in the east-west direction u, divided by zi, where zi is the roughness length, which is essentially the height above the surface of the planet where the wind speed actually goes to 0. And then the north-south component is the same, except for you have the north-south wind v. So we have these different forces, but not all of the forces are as large as each other. They each have different magnitudes. And geostrophic balance represents a flow in which the pressure gradient force is balanced by the Coriolis force, and all of the other forces are essentially considered to be negligible. So in this case, in the figure shown here, we have the pressure gradient force, which is pointing directly from high to low. We have the velocity vector, which is pointing to the right. So the air parcel wants to accelerate from high to low, but it's deflected to the right by the Coriolis force. And eventually, as the wind speed gets stronger, the Coriolis force gets stronger. And eventually the Coriolis force will be large enough to completely balance the pressure gradient force. And in this balanced flow situation, you have wind that is blowing parallel to the isobars. And we refer to this as geostrophic balance. In geostrophic balance, the air never crosses the isobars. The highs never get weaker. The lows never get stronger, basically. And you just have a static situation. So geostrophic balance is a diagnostic form of the horizontal momentum equation and not a prognostic, which means that you can't use geostrophic balance in order to predict the future of the wind field at some time in the future. So here we have an example of the geostrophic wind. So we have high pressure on the left, low pressure on the right. Air wants to flow from high to low in the northern hemisphere here, and the air is being deflected to the right because we're in the northern hemisphere, and the wind will end up blowing parallel to those isobars, and the strength of the wind will be directly related to the how close the isobars are together. So basically how big the pressure gradient is. So in this case, you have a strong pressure gradient on the right and a weaker pressure gradient on the left. As a result, you have stronger winds on the right, weaker winds on the left. The geostrophic wind equations, if you want to solve for the U component of the geostrophic wind, in terms of the pressure gradient, it's -1 over rho times the Coriolis parameter times delta P over delta Y, not X, delta Y. You can also write the geostrophic wind in terms of the gradient of the geopotential phi, or you can write it in terms of the gradient of the geopotential height, h. And you just have slightly different constants out in front. So when you're using the geopotential phi, then the constant out front is 1 over the Coriolis parameter. And when you're dealing with the geopotential height, then it's g naught, which is the force of gravity divided by the Coriolis parameter, times delta h over delta y. And then for the geostrophic wind, the north-south component, Vg, is just similar, except for the sign is no longer negative. And instead of being delta P over delta Y, it's delta P over delta X, and delta Phi over delta X, and delta H over delta X. And generally speaking, the geostrophic flow is a really good approximation for the winds in the atmosphere once you get above the friction layer, that is to say, once you get above the atmospheric boundary layer. A different type of balance, which involves three forces, a balance of three forces, would be the gradient wind. And here we're going to have a balance of the pressure gradient force, the Coriolis force, and now we're going to add in the centrifugal force. And recall that the centrifugal force is going to be pointed out from the radius of curvature. And near a trough, so this is a low pressure zone, the wind slows down because the Coriolis force is combining with the centrifugal force to balance the pressure gradient force, and the wind speed doesn't have to be quite as strong for the Coriolis force. The Coriolis force doesn't have to be quite as strong, which means that the wind speed doesn't have to be quite as big. And however, around a high pressure, the centrifugal force is in the same direction as the pressure gradient, and as a result, the wind is going to have to be stronger than the geostrophic wind in order to compensate, so that you have a Coriolis force that will balance both of those forces. And so near the ridge, the wind is going to speed up, and the wind will be a little bit faster than geostrophic. The gradient wind is still parallel to the isobars. It's just either stronger or weaker than the geostrophic wind, depending upon whether or not it's rotating around a low pressure zone or around a high pressure zone. The equation for the gradient wind balance, essentially we have a balance of these three forces. We have the pressure gradient force, the Coriolis force, and the centrifugal force. You have essentially seen all of these terms before, and now we're just putting them together into a single equation. And As mentioned before, the gradient wind is important for regions of strong curvature near high and low pressure centers. In the boundary layer, we often have friction. I mean, that's kind of the definition of boundary layer. And friction will tend to slow down the air, which will cause the Coriolis force to be slightly less. And here we have a balance of forces where the pressure gradient force is balanced by a combination of the Coriolis force and the frictional force. So you add the frictional force and the Coriolis force together, and they will exactly balance the pressure gradient force. And the net result when this happens is the wind vector that's shown in gray here, MABL. That is the wind that is actually crossing the isobars from high to low, and they have a cross-isobaric flow angle of alpha. And the stronger the frictional force, the larger the cross-isobaric flow angle will be. So in mountainous terrain, the cross-isobaric flow angle can be 45 degrees or more. Over the oceans, the cross-isobaric flow angle is often only 5 to 15 degrees. So there's not a lot of friction over the ocean, whereas there is over mountainous terrain. So that three-way balance near the surface is really just friction slowing down the wind speed, and that the friction itself doesn't change the wind direction, but the balance of forces actually does and causes the cross-isobaric flow. So we have air that crosses the isobars from high to low. This will cause the low pressures to not be as strong, and it will cause the high pressures to weaken. And so basically it does allow for the evolution of high and low pressures, because you're able to move mass from one column of the atmosphere to another because of the cross-isobaric flow. So here's an example of air that is rotating around a low pressure zone in the northern hemisphere. It's rotating counterclockwise, and you can see that there is a cross-isobaric flow component in all of these arrows that are drawn, and that means that there's actually a little bit of surface convergence at the middle of this low pressure zone. And if you have surface convergence, that will lead to vertical motion. So as seen here on the right, if you have that surface-based convergence, the air can't move through the ground, so its only option is to move upward, and we'll end up with rising motion over the low pressure zone. And consequently, in the high pressure zone, as air is crossing the isobars from high to low, you have divergence at the surface. And as you have divergence at the surface, air will rush in from above in order to fill that void, causing subsidence over the high pressure zone. And that will cause essentially clear skies over the high pressure zone and cloudy skies over the low pressure zone. And the last balance that we're going to talk about is cyclostrophic balance. And the cyclostrophic balance occurs when the pressure gradient force is balanced by the centrifugal force only. And here we have the centrifugal force, which is outward directed, the pressure gradient, which is inward directed to this low. And in order for this to happen, the circulation has to be short-lived or small enough to where the Coriolis force becomes negligible. And the equation for the cyclostrophic balance is just the balance of these two forces, the pressure gradient and the centrifugal force. These two parts of the horizontal equation of motion. And what do we know about the cyclostrophic wind? Well, it's basically can describe small-scale circulation such as tornadoes, waterspouts, and dust devils that are short-lived enough that the Coriolis force can be neglected. And the cyclostrophic balance doesn't have a preferred rotational orientation. It can occur regardless of whether or not it is rotating cyclonically or anticyclonically around the center of rotation. So dust devils basically and waterspouts typically have about 50-50 on whether or not they're rotating clockwise or counterclockwise. Tornadoes in the northern hemisphere, in the United States anyway, do not have a 50-50 balance. They are actually 90% cyclonically rotating, and 10% anticyclonic. So basically 90% rotating counterclockwise and 10% rotating clockwise. But the reason for that is that if you remember with these thunderstorm formations, when we have the horizontal vorticity or rotation in the Earth's atmosphere that gets tilted into the vertical, and then we have the left moving storms and the right moving storms. Well, as it turns out, those right moving storms are the ones that preferentially survive, and they also happen to be the ones that are rotating counterclockwise. So that is more a function of which of the storms survive, the left moving or the right moving, rather than the impact of the Coriolis force at all.